Hello, everybody. This is Mr. McAllen, and today we're going to be talking about working with differentials and understanding when to use a differential. Well, let's just take a moment to understand what a differential is. A differential is basically a difference, but in calculus, we're going to be able to do much more than just a difference. Let's take a look at an example and say that we want to work with finding the difference in the volume of a basketball when the ball swells from a radius of 10 inches to 10.1 inches. How does the volume change? Without calculus, we would just do the volume at 10.1 and we plug that into equation and we have 4/3 pi times 10.1 cubed. And we would find the volume when it was 10, and that would be 4/3 pi times 10 cubed. We could go to a calculator and compute what the volume at 10.1 was, which we would have to go use a calculator to do that. So that would be 10.1 to the third power, which would be 4/3 pi times 1030.301. And then the volume at 10 would be 4/3 pi times 1,000. And when we take the difference of these, we would find the change in volume. So I'm just going to calculate that and I'll come back with the answer in a moment. So let me just pause. So after a couple minutes of computations using my calculator, we find that the difference in the volume was 127.04 inches cubed. So now I'm going to introduce the idea of using a differential, and it's relatively quick to do. If I take the derivative with respect to the independent variable, which is radius, and I get the derivative of the volume equation is just a simple polynomial derivative. I bring the 3 down in front of the 4/3 pi r. I have to reduce the power of 1 squared. I get the derivative. Now, using this notation, I'm allowed to solve for the differential change in volume. And did you notice I said the word differential change in volume, which is equal to, when the 3's cancel, 4 pi r squared. Remember, this is dV/dr. And I'm allowed to, through the use of this notation, multiply both sides by dr. And now I have an approximate form of the change in volume. So look at how easy this is. I'm going to find my approximate, now notice I'm saying approximate change in volume, because this is based on a linearization. But let's look at how accurate it is. The change in volume is equal to 4 times pi times the original radius I had. Now notice I didn't put 10.1 in there, I just put 10 in. I'm going to square it, but here where I have the dr, that represents the change in the radius. So I'll put in 0.1. Now, when I calculate this out, the volume change is equal to 400 pi, because 10 squared is 100, times 0.1, which when that gets multiplied out, I get 125.667 inches cubed. Now, it is not the same as the actual change in volume. Notice it's off by a little bit, but that's what happens when you use a differential. You get a quicker calculation for a change in something, but it's only an approximation. Let's take a look at another example. if my function is the sine of 2x, then find out how much the function changes when x equals pi and x changes by 1/100th. Basically what we're saying here is if x equals 3.14159 and it increases to the change in x is 0.01, making the new value of x 3.15159, how much does the sine function change? So that's what we're going to work on. So I have my function f of x is equal to the sine of 2x. And remember, a differential uses the derivative. So let me take the derivative, df dx, and that's going to equal the sine of 2, the derivative will be the cosine of 2x, and don't forget the chain rule. So now df dx is equal to 2 cosine of 2x, and if I want to find out what my change in function value is, that would be df by cross multiplying. I have 2 cosine of 2x times the change in x. So let's check this out. df, the change in f, the approximate change, because it's using a linearized differential, is going to be 2 times the cosine of 2 times, remember this is going to be pi, because the x value is the original, and dx is going to be the amount that it changed. So does everybody know what the cosine of 2 pi is? You should know that's equal to, the cosine of 2 pi is equal to 1 times 0.01. So I'm expecting a change in my function value to be equal to 0.02. Let's see what happens when we check this out, when we do this with the actual function. So I'm going to go to Desmos and I'm going to put in this function, and I'm going to look at where it exists at pi, and I'm going to see how much it changes when x changes by 0.01. So I'm just going to pause the video and change over to Desmos and set that up. Okay, well, we're back, and I switched over to Desmos, and as you can see here, I have the plot of the sine of 2x. The sine of 2x is showing that the function changes from well, it doesn't, it's the sine of 2x, but you can see two frequencies from 0 to 2 pi, which is consistent with the frequency inside the function. And you can see that at x equals pi, the sine value has a value of 0. So, as we said before, when we work with our differential calculation, if the x value changes by 0.01 radians, the function value should change by 0.02 units. So going back to Desmos, I'm going to just plug in here, I'll type in pi plus 0.01, and when you add plus 0.01, you can see that the function value has changed from 0 to 0.019998, just almost exactly 0.02 units, just like the differential predicted. And if I went down by if let's say I typed in pi minus 0.01, so that the amount was in the opposite direction, you see that my function would have changed by negative 0.02 units, thus showing that the differential df, taken from just a simple calculation or cross multiplication of the derivative by finding df dx like we always do, and getting what the derivative is, which is 2 cosine of 2x, by just cross multiplying that dx term over, we can now calculate what the change or the change in the function would be. And this is quite incredible as far as for figuring out a quick way to figure out a change in a function as opposed to doing all this work that we did before where we'd have to find the volume at 10.1 and we had to find the volume at 10.0 and then we'd have to find the change in volume. And all of that work we did calculating to get 127.04, when if we use just the derivative, we could have calculated a quicker approximation. We would have sacrificed some accuracy, but we would have gotten an answer much quicker through the use of calculus. I hope this video helps you understand why we use differentials, and I look forward to making another video in the future to show you some more examples of differential use.